Lesson: Unsupervised Learning Concepts and Models. Unsupervised learning is a fundamental concept within the realm of machine learning, distinct from its counterpart, supervised learning, in that it does not rely on labeled data. Instead, unsupervised learning algorithms are designed to identify patterns, structures, and relationships in data without prior knowledge of the outcomes. This approach is invaluable in situations where data labeling is prohibitive due to cost or complexity, making unsupervised learning a key tool for discovering hidden insights and fostering innovation in data analysis. At the core of unsupervised learning lies its ability to discern the inherent structure of data. Clustering and dimensionality reduction are two primary branches of unsupervised learning, each with distinct applications and methodologies. Clustering is the task of grouping a set of objects in such a way that objects in the same group, or cluster, are more similar to each other than to those in other groups. The most widely used clustering algorithm is k-means, which partitions data into k-clusters by minimizing the variance within each cluster. K-means is particularly effective for large datasets, as it is computationally efficient and easy to implement. However, it requires the user to specify the number of clusters in advance, which can be a limitation if the optimal number is not known a priori. An example of k-means in action is customer segmentation in marketing. By clustering customers based on purchasing behavior or demographic data, businesses can tailor their marketing strategies to target specific segments more effectively. This approach has been shown to increase customer engagement and retention, leading to improved business outcomes. Additionally, k-means can be integrated with visualization tools such as PCA to enhance interpretability and provide actionable insights. Another powerful clustering technique is hierarchical clustering, which builds a tree of clusters, allowing for different levels of granularity in data analysis. Unlike k-means, hierarchical clustering does not require a predetermined number of clusters. It is particularly useful for exploratory data analysis and provides a visual representation of the data's structure through dendrograms. For instance, in genomic studies, hierarchical clustering can uncover relationships between genes or samples, providing insights into genetic variations and potential pathways for disease. Dimensionality reduction is another critical aspect of unsupervised learning, aimed at reducing the number of random variables under consideration by obtaining a set of principal variables. Techniques such as PCA and TSNE are commonly used for this purpose. PCA transforms data into a new coordinate system, with the greatest variance on the first coordinate, the second greatest on the second coordinate, and so on. This method is particularly useful in pre-processing stages to reduce data dimensionality while preserving as much variance as possible, facilitating easier and more accurate data visualization and analysis. TSNE, on the other hand, is more suited for visualizing high-dimensional data in a 2- or 3-dimensional space. It is particularly effective for datasets with nonlinear relationships, where PCA might fall short. TSNE has been widely adopted for visualizing complex datasets such as those found in image recognition and natural language processing, allowing for the discovery of patterns and structures not easily discerned with other methods. In practical applications, the choice between PCA and TSNE depends on the specific requirements of the task at hand. For instance, PCA might be preferred for its simplicity and speed when dealing with very large datasets, while TSNE is often chosen for its superior visualization capabilities in smaller, complex datasets where preserving local structures is crucial. A significant real-world application of unsupervised learning is anomaly detection, which is essential in fields such as cybersecurity, finance, and healthcare. Unsupervised anomaly detection techniques, such as isolation forest and dbScan, identify outliers in data that deviate significantly from the norm. Isolation forest is particularly efficient for high-dimensional datasets, as it isolates anomalies rather than profiling normal data points. In cybersecurity, anomaly detection can be used to identify unusual patterns in network traffic that may indicate a security breach, enabling prompt and effective responses to potential threats. dbScan, a density-based clustering algorithm, is adept at discovering clusters of varying shapes and sizes, including identifying noise and outliers. It is particularly useful in spatial data analysis, such as identifying geographical clusters of disease outbreaks. By analyzing spatial data patterns, public health officials can implement targeted interventions, ultimately saving lives and resources. Implementing unsupervised learning models requires a robust understanding of the data and the specific challenges at hand. The process typically begins with data preprocessing, which involves cleaning the data to handle missing values, normalizing features, and, if necessary, performing dimensionality reduction. Practical tools such as Python's scikit-learn library provide comprehensive support for preprocessing, clustering, and visualization, making it a popular choice among practitioners. Once the data is preprocessed, the next step is selecting an appropriate model. This decision is guided by the nature of the data, the desired outcomes, and computational considerations. For instance, if the task involves clustering customer data to enhance marketing strategies, K-means might be the model of choice for its efficiency and ease of interpretation. Conversely, if the goal is to visualize complex biological data, TS&E could be more appropriate due to its capability to preserve local similarities. After selecting a model, the next phase involves training the model on the data. This step often requires tuning parameters, such as the number of clusters in K-means or the perplexity parameter in TS&E, to optimize performance. Tools like Grid Search CV and scikit-learn can automate this process by exhaustively searching for the best parameter combination, saving time and improving results. Evaluation of unsupervised learning models poses unique challenges, as there is no ground truth to compare against. Instead, evaluation often relies on metrics such as silhouette scores for clustering, which measure how similar an object is to its own cluster compared to other clusters. For dimensionality reduction, visualization and interpretability are key factors in assessing effectiveness. Despite its challenges, unsupervised learning offers immense potential for generating insights from complex data. As data continues to grow in volume and complexity, unsupervised learning techniques will become increasingly vital for organizations seeking to unlock the full value of their data. By integrating these techniques with practical tools and frameworks, professionals can enhance their proficiency in unsupervised learning, addressing real-world challenges with innovative solutions. In conclusion, unsupervised learning is a cornerstone of machine learning, offering powerful tools for discovering patterns and structures in data without labeled examples. Through clustering and dimensionality reduction, unsupervised learning enables the extraction of meaningful insights from complex data sets. Practical applications across various industries demonstrate its versatility and potential for driving innovation. By mastering the concepts and models of unsupervised learning, professionals can implement these techniques effectively, harnessing the power of data to inform decision-making and foster growth.